Welcome to this new video of mathematics and economic modeling, Math-S400. So in the previous lectures we saw the concept of a sequence of real numbers and then convergence of this sequence of real numbers to some number. And then we also saw the concept of a subsequence, and we have shown that every bounded sequence has a convergent subsequence. This is the so-called Bolzano-Weierstrass theorem. So the main goal of today is to define or to generalize the notion of a sequence of numbers towards a sequence of vectors, and then to see an equivalent of the Bolzano-Weierstrass theorem not for sequences of numbers but for sequences of vectors. In particular, we will show that every sequence of vectors that's bounded, in some sense that I will define in a few minutes, has a convergent subsequence. Okay. So let me go to the notes. So we want to introduce the concept of a sequence of vectors. Well, the notion is very similar to a sequence of numbers. So remember, we had the set of natural numbers 1, 2, 3, 4, 5, 6, and so on, right? They go infinitely long. So there's no end to the sequence. And then to every number here we associated, if you wanted to talk about sequences in R, we associated a number. So here the first number was x1, second number you can call it x2, then the third number is x3, x4, x5. Okay, so this is a sequence of numbers, and there's no limit to this, the length of the sequence, right? So this goes on forever. Now, sequence of vectors is very similar, except that we don't have numbers in the sequence, but now we have vectors. Okay, so elements of Rk. So this could be a first vector, this could be a second vector, this could be a third vector, a fourth vector, a fifth vector, and so on. Okay, so it's important that all these vectors are of the same dimension. Okay, so we don't have a vector that's of size 2 and then one of size 3 and then one of size 7 and so on and so on. Okay, so they're all the size, same dimension, k, but they're all vectors, right? They're no longer numbers. So x1 could consist of k numbers, right? So this is a vector existing of k numbers, this is a vector consisting of k numbers, and so on. Okay, so these are all now vectors. Okay, so the definition of a sequence of vectors is very similar to the sequence of numbers. So remember that we defined a sequence in R to be a mapping f, say f, from the natural numbers to the real numbers, right? So for every natural number we associated a real number. Well, now a sequence in Rk is simply a mapping from n to the set of vectors in Rk. Okay, so for every number we associate a vector. Okay, good. So that's nothing very strange. So we just generalize the concept. We go from numbers to something of higher dimension, which is just k numbers. Okay. Okay, so now we have this, find this sequence, and similar to before. So for sequences of numbers, we never use this notation. Remember, we used the notation xn and n. Well, we will do something similar for sequences of vectors. We will use this notation for a sequence of vectors. Okay. So we had also the notion, similar, we had the notion of a sequence of numbers to converge to a number. Right, remember the sequence of numbers xn converges to a number x and r if the following definition was satisfied. So for every epsilon bigger than 0, there was a number n epsilon that is in the natural numbers, and then for all small n greater or equal to this n epsilon, the distance between xn and x was smaller than epsilon. Okay, so this was the definition of convergence of a sequence to R. Now the convergence of a sequence of vectors is very similar, so we have to make a few changes, of course. So we're not talking about the sequence of numbers, but we're talking about the sequence of vectors. And the sequence of vectors doesn't converge to a number, but it converges to a vector, which is now in, let's say, in Rk. Okay, now this can all stay, but here we have to make some changes, right? So the numbers have to become vectors. And now this here is a vector, right? It's the difference of two vectors. The absolute value of vector, I don't really know what this is, but we can imagine something, but it has to be smaller than a number, right? So here on the left hand side, you also would like to have a number that somehow measures the distance between this vector and this vector. Okay, and you already have seen the concept that you can use for this. Basically, the distance between these two vectors, this is simply the norm of xn minus x. Okay, so this is the definition that you use for convergence of a sequence of vectors to a vector x. It simply says that for all epsilon there exists an n such that for all small n bigger than this big N, right? So if you go far enough into the sequence, you will find this big N, and anything beyond will be epsilon close to this limit here, right? Because this is the distance between these two vectors. Okay, so the distance between the sequence xn and the limiting vector x goes to 0. And you see that this is simply a number, right? So we can, for example, call this the number yn. Okay, so from this it's easy to see that the sequence xn will go to x. This is notation that we will use, is the same as saying that the sequence yn of these numbers converges to 0, right? So basically everything goes back to convergence of some sequence to 0. And here the sequence is the sequence of yn, which is simply the distance between xn and x, right? So if this sequence of numbers goes to 0, then we say that the sequence of these vectors converges to this vector. Okay. So this is the definition of a sequence of vectors, convergence of a sequence of vectors, which is very similar to a sequence of numbers, except that you have to make a few changes to the definition. And you also have seen the concept of a subsequence. Okay, so remember 1, 2, 3, 4, 5, 6, 7. We again have the natural numbers, and then we had our numbers in R, x4, x5, x6, x7, and so on. So how did we envision a subsequence? Well, we again have the set of natural numbers, and we had a mapping from the upper natural numbers to the lower ones, right, such that no one of these arrows crosses. Okay, so for example 4 goes to 6, 5 goes to 8, and so on. So this was our function phi, remember. My video went dead. Okay, and then we had the normal mapping, fourth element, and so on. Okay, so this generated a subsequence. In particular, this was the first element of the subsequence, and then this was the second element of the subsequence, and then this was the third element of the subsequence, the fourth element, and so on. Okay, so in general, the nth element of the subsequence was x phi of n, right? Phi of n was the mapping from here to here, and then the x of phi of n is this element. Okay, so for a sequence of vectors, it's almost identical, right? So the only thing that changes is that these things here become vectors and no longer numbers. Okay, so we have a mapping from numbers to numbers and then to a vector, so this will be denoted, we will denote our subsequence of vectors like this. Okay, so all the concepts of sequence of numbers and R naturally extend to sequences of vectors, right? This is now okay. So basically there's a direct analogy. And then you had to remember the Bolzano Bolzano-Weierstrass theorem that says that every bounded sequence in R has a subsequence that converges, right? So it has a convergent subsequence. Okay, and they use this concept of tops, right? There are only infinitely many tops, then you have the sequence of tops that converges, and there are only finitely many tops, and basically we could generate a sequence that also converges. So the main idea of the remainder of this lecture is to show that this generalizes to sequences in Rk, right? So if we have a sequence of vectors in Rk, then you can find a subsequence, something like this, right? So we can pick some elements out of the subsequence such that the subsequence converges. So one thing that we still have to generalize is this idea of a bounded sequence. Okay, so remember a sequence of numbers was bounded if we could find a number m. So xn is bounded. Okay, if you could find an m such that for all n the absolute value of xn was smaller than m. Right, remember if we draw the line, then if we had m and minus m, every element of the sequence was in this interval between m and minus m. Okay, so we would like to generalize this to vectors. Well, there's a simple way to do this. Well, this can stay. The only thing that now we have to change is this xn has to become a vector, and we're not talking about the absolute value anymore, but we're talking about the norm. Okay, so in particular, what does this mean? Let's go to 2 dimensions. Okay, so the vectors live in, if you have 2-dimensional vectors, then they live in 2 dimensions. So all the vectors whose distance from 0, right? So this is the distance from 0 from xn is smaller than m. So how can you find them? All the vectors whose distance from 0 here are less than m. Well, if I try to draw a sphere, which is not very well, but this is a sphere, right? If I draw a sphere of radius m, then this means that every vector has to be within this sphere, circle, right? It's 2D sphere is a circle for your information. Okay, so every vector, 2-dimensional vector, has to be within the circle, within the area of the circle. Okay, so that's the definition of bounded. You cannot go out this circle. If you have 3 dimensions, you have a sphere of radius m, right? So there has to be some sphere such that everything in the sequence stays within the sphere, right? So you cannot escape to infinity. So this is the notion of boundedness that we will use. Okay. So we have to show that every bounded sequence in Rk has a convergent subsequence. Okay, so Bolzano-Weierstrass theorem, this I have rewritten it a little bit in a different way. So Bolzano-Weierstrass basically says that for all sequences in Rk, if the sequence is bounded, then you should be able to find a subsequence x, phi, n that converges, right? And this is a subsequence of this sequence. Okay, so we're going to prove this theorem, and we're going to use a proof which might be a little bit strange at first sight, but we're going to use the proof by induction. Okay, and the induction here is going to be on the dimension k. Okay, so basically what you can say is you can say that this theorem basically says that for all k and n, and for all sequences in Rk, if the sequence is bounded, then there exists a subsequence that converges, right? So we want to prove this for every possible dimension that we can think of. So we're going to prove this for every k, and we're going to do induction on this k. Okay, remember, if you want to prove by induction, you need to count over the natural numbers, and this is going to be the natural numbers that we will look at. Okay, so in order to do proof by induction, we need 2 things, right? We have to prove the base case, which is when here k is equal to 1. and then you have to prove that if this holds for pk, then it also holds for pk plus 1. Okay, so the A will be, so if this is our formula pk, okay, so here's the k, this is where the k enters, so we have to prove p1, right, for k equal to 1, and then you have to show b that for all k and n, if pk is true, right, if every sequence in Rk which is bounded has a convergent subsequence, then every sequence in Rk plus 1 that is bounded also has a convergent subsequence. Okay. P k plus 1. Okay, so this is the proof strategy that we will use to prove this. Okay. So first, let's look at A. Try to prove for k equal to 1. So what do we have if k is equal to 1? Then you have every sequence of vectors in R1. And what's R1? Well, R1 is simply the set of real numbers, right? So basically it says that for every sequence in R, if the sequence is bounded, then there exists a convergent subsequence. But we already know that this is true because we proved Bolzano-Weierstrass for sequences of real numbers. And if k is equal to 1, then basically we have a sequence of real numbers. And for this we already know that every bounded sequence has a convergent subsequence. Okay, so A, basically done, right? We already proved this. So C, previous lecture. Right, remember the proof with the tops and the infinite tops and the finitely many tops. Okay, so this was the proof for k equal to 1. So we already did the heavy lifting for this case. So now let's look at B. So what do? We assume that this theorem holds up to k. Okay, and you want to prove it for k plus 1. So what do we need? We need to prove that this holds for every sequence in Rk plus 1. So take a sequence and let's call this x n and Rk plus 1. Okay. So we take a sequence, any sequence, right? It has to hold for every sequence. So take any sequence. If you can show it for any sequence, then you have shown the theorem. Okay, so we take any sequence in Rk plus 1. So let's write down the first few elements of the sequence. Okay, so we have x1, you have x2, you have x3, and so on. Okay, so this sequence is a sequence in Rk plus 1, so basically it consists of k plus 1 numbers. Okay, so maybe this is x1, 1. Okay, so the first number is going to be the number of the sequence, and the second number is going to be the element in the vector. Okay, so the second element of x1, the third element of x1, and so on, the kth element of x1, and then you have a final one, x1 k plus 1, because it's of dimension k plus 1. Okay, and you can do the same thing for x2, x21, x22, and so on, x2k and x2k plus 1. You can do the same for x3, x31, x32, x3k, and x3k plus 1, and so on, and so on, and so on. Okay, so that's our sequence of vectors of dimension k plus 1. And remember, we know something about sequences of vectors of dimension k. So what we're going to do is the following. We're going to take the first k element in every vector, right? These are of dimension x, of dimension k, and then we're going to look at the last element in every vector. Okay, so here let's take the first k elements in this vector and let's call this the vector y1. Okay, so basically what we do, we have a vector of k plus 1 elements, we leave out the last one, and then the first k elements, this is going to be a new vector, right, existing of k elements, and we call this y1. This is what we're going to call y2. This is what we're going to call y3, right? So each time we take the first k elements, we have y4, and so on and so on. And then the last element here, let's use some other notation. Let me call this z1 and z2 and z3 and so on, z4 and so on. Okay, so this is what we're going to do. So if you look at y1, y2, y3, y4, every one of these vectors have dimension k. So we know that yn, this sequence of vectors, right, it never ends, is a sequence in Rk. Okay, and then if you look at the z1 is a number, right, it's this number here. Z2 is a number, it's this number here. Z3 is a number, and so on. So Zn is a sequence in R. Okay, so basically what we did, we had a sequence of vectors in Rk plus 1, and every vector we split it up into a vector of size Rk and then a number, right? We just tore every vector apart into two, and then all the first parts form a sequence in Rk, and then all the latter parts form a sequence in R. And you would like to use induction on both of them, right? So in particular, let's start by trying to use induction on this one. Okay, so this is a sequence in Rk, right? We assume Pk, so we know if this is bounded, okay, if this is bounded, then we know this has a convergent subsequence. Okay, so the first thing that we're going to show now is that this sequence of yns is bounded. So let's first show that yn is bounded. Okay, so this is actually not so difficult, right? So let's take the norm of yn. Okay, so what's this? This is the square root of the sum 1 to k of, so yn consists of xn1 to xnk, right? So we can immediately fill in. So this is xni squared. Okay, so here we sum from 1 to k. If we add the last non-negative term, this can only grow, right? So this is what we're going to do. We're going to now take the sum for 1 to k plus 1 of xni squared, and this is the norm of x and the vector xn. Okay, remember this was the vector xn, so the norm of xn is simply here, the sum of the elements squared and then taking the square root. As the sequence is bounded, okay, so we have to show that every bounded sequence converges, right? So we take a sequence here, I forgot it, take a sequence xn that is bounded. Okay, sorry for this, right? So we can assume that it's bounded, then you have to show that it has a convergent subsequence. So as this sequence is bounded, I know that there exists an M such that xn is smaller than n. Okay, and as the norm of yn is smaller than the norm of xn, so I know that norm of yn is also smaller than m, so this sequence yn is also bounded. Okay, so what do I have? I have that yn is a sequence in Rk. I know that Yn is bounded, so if I assume Pk, right, so this was what I assume it holds for Pk, then I know that Yn has a convergent subsequence. Okay, so far so good. So it has a convergent subsequence, so let's say that y phi n, which is now the subsequence of this sequence of vectors, converges to some Yn Rk. Okay, so this is where the induction kicks in. So remember, x was defined like a vector y and a vector z. Okay, so let's try to write it again in this way. So we had x1, so let's write it x1, x2, x3, and so on. This was the vector y1 and then a number z1. This was the vector y2 and then a number z2. This was the vector y3 and then the number z3, and so on. Okay, and here we have found the subsequence of y's. So what are we going to do? We're going to look at where is y phi of 1. Okay, it could be the first element, the second element, or the third element, and so on. Right, so we're going to look at the particular y phi 1. Okay, and of course, for example, this is the 10th element in this sequence. Right, so here I have y10. Right, this is the 10th element in the sequence. Of course, I have a z10 and I have an x10. Okay, so if phi of 1 is equal to 10, then z10 will be z phi 1, and this will be associated with the vector x phi 1. Okay, I can look for the second element in this sequence, in this subsequence. For example, it's 20 or 30 or 25 or whatever. I don't really know. Right, so this is y phi 2. In the same vector, I have a z phi 2. And this is associated with x phi 2. Okay, I can find the third element, x phi 3, which is basically y phi 3, z phi 3. Okay, so all these are, of course, vectors. All right, so basically what I can do is I can look at this subsequence of y's and get the x's and the z's that correspond to it. All right, so if the phi 1 is 10, then I look at also a z10, and this together then makes x10. If phi 2 is, for example, 20, then I can look at the z20, and y20 and z20 make x20. If phi 3 is, for example, 100, then I can look at the z100, and y100 and z100 make x100, and so forth and so forth. Right? So this is the sequence that we're going to continue working with. So let me copy it back here, because it's quite important. Z phi 2, y phi 3, z phi 3. So I can write out all these vectors. Okay, so this is x phi 1, this is the vector x phi 2, this is the vector x phi 3, and so on. Okay, so basically this is the original sequence, but only limited to this subsequence of y's, right? So we take the phi's that are associated with this subsequence, and we restrict all the z's to this thing here. So what do we know? We know that this vector here, this sequence of vectors, converges to a vector y. Okay, so this sequence of vectors will converge to some vector of 2y. Okay. So what about this sequence of numbers? Well, you haven't said anything about convergence of this sequence, right? I have no idea. It could go to infinity, it could go to 0, it could go to number, it couldn't converge at all. It could go up and down, up and down, up and down, or go nowhere. So if you want this to converge to something, right, we would like a subsequence of the x's, so this could be one subsequence. If we want this to converge to something, we better have this, the latter one, also converge to something. Okay, so it's a bit, what do we do now? Well, the idea is actually quite simple. So look at this subsequence of the z's. All right, so this subsequence of the z's is also a sequence in R, right? A subsequence is also a sequence. It goes forever and ever and ever and ever and so on and so on. So in particular, if you can show that the sequence is bounded, it also has a convergent subsequence. So let's do this first. So let's show that z phi n is bounded. So how can you show that this is bounded? Well, we have z phi n. So this is equal to z phi n squared, and then taking the square root. So in particular, z phi n is the same as, remember, it's the phi nth vector x, and then we took the k plus 1th element, right? Okay, so if phi is equal to 10, then you have x 10 k plus 1. And then we square it, and then we take the square root. So this is of course smaller than if I would take the square root and the sum of all the x's. I, right? Have to be a bit careful. Squared. And this is nothing else than the norm of x phi n. And I know that there exists an M such that x phi n is smaller than m because the sequence x is bounded. And I hope you understand that if the sequence is bounded, then any subsequence of the sequence will also be bounded, right? If I have a sequence that lives in this ball around 0, and if I take a subsequence, then the subsequence also has to live within this ball around 0, right? Nothing of x can, the sequence xn can go outside this ball or this circle, and of course nothing about the subsequence can also go out the circle. Okay. So we have that z phi n, absolute value of z phi n is also smaller than m. So z phi n is bounded. So we have a sequence of numbers. Z phi n is a sequence in R, and you have the sequence is bounded. So by P1, okay, I have to look at the formulation of my Bolzano-Weierstrass theorem, right? So here's it back. So we already proved P1, right? Remember, in the previous lecture. So this is basically a sequence in Rn that's bounded. So Z phi n, this sequence, has a convergent subsequence. Okay. So this convergent subsequence is a subsequence of this subsequence. All right, so it's two subsequences. So we take a subsequence, right? We delete some elements of the original sequence, and then from the subsequence we again delete some elements of the sequence, and the resulting sequence that we will get will be a convergent sequence. So you can call it a subsequence if you want. So how do we denote it? Well, remember, Z phi n was a subsequence, So basically what we do, instead of n, we need to take a function of this n, right? A function from n to n, which doesn't cross as before. So let us call this this function, let's call this psi. Right, so basically we have a sequence z phi of psi of n. Okay. So for example, if right, so if this is, now you have to look at it 3 stages far, right? So this is a z1, z2, z3, z4, z5, right? This was the original sequence. Then we took a subsequence of this original sequence, a phi, for example, 1 to 2, 2 to 4, 3 to 5. Okay, so this was phi, and now we have to put a subsequence on top of this one. So for example, here 1 goes to 2, and 2 goes to 4, and so on. So let me get a number, another 6 here, and a 7. And for example, let 5 go to 7, and 3 go to 5, right? So at least we have some examples here. Okay, so what do we have? We have phi. What's the first element of the subsequence, right? So we can see this by following this here. Goes to 2, 2 goes to 4. So Z4 will be the first element of the subsequence. 2, 2 goes to 4. 4 goes to, I forgot to put an arrow from 4 to something. Let's say 6. So where's my green? Okay, to 6, this goes to Z6. The third element goes to 5, and then from 5 to 7, so this is Z7. Okay. So for example, if I look at Z phi of psi of 1, psi of 1 is 2, right? Phi of 2, right, is 4. So Z of phi of psi of 1 will be equal to Z4, which is the first element of my subsequence. Okay, so this is basically how it goes. We put another subsequence on top of this already existing subsequence. Okay, so this is a notation. It's a bit of an ugly notation, but this is notation, and we know that this subsequence converges, right, from the Bolzano-Weierstrass of sequences of real numbers. So we have Z of phi of psi of n. This converges to some Z in R. Okay. So let's look at Z of psi of phi of 1. Then we have the second element Z of phi of psi of 2, and Z of phi of psi of 3. Okay, all the Greek. I didn't study Greek, so I don't know a lot about this. Right? So for every Z, for example, if this is the fourth element, we can also look at Y of the fourth element. Right? And this, of course, should still be a Y that's in the subsequence Y of phi. Okay, so we can look at Y of phi of psi of 1. Y, so this is a Y, it's not a psi, over a phi of psi of 2. Y of phi of psi of 3, and so on. Okay, so basically we look at the associated vector of y's that correspond to this subsequence, and this is x of psi phi of psi of 1, x of phi of psi of 2, x of phi of psi of 3, and so on. Okay. So now we basically will look at the subsequence of a subsequence of the x's, right? We have first taken a subsequence for the y's, and now we take a subsequence of the z's. So if you look at the subsequence of the y's, we had that this subsequence converges to y. Okay, and now we take a subsequence of this subsequence. And of course, if a sequence converges to y, and you throw away some elements, whatever remains will also converge to the same thing. Okay? Because you keep infinitely many elements of this original sequence. Okay, so whatever is left from the sequence here is a subsequence, but this subsequence will still converge to the same y. And also here, this z, which we now know converges to this number z. Okay, so both subparts of x's that are vectors converges, the y's, and also the last row also converges to this z. And what we can do is we can put this y and we can put this z into a vector of dimension rk plus 1, and we can call this the vector x. So this is a definition of a vector x. And the idea will be that because this sequence of vectors converges to this, and this sequence of vector numbers, converges to this, and then this sequence of vectors will converge to this. Okay, so this is what we're going to show finally now, and this is going to finish the proof. So in order to show convergence, you have to show that this minus this, the norm of this here, goes to 0. Okay, so we're going to use the convergence lemma. So we're going to say that if n is big enough, then this will go to 0. So how do we do this? Well, let's write out back in terms of y and in terms of the z here, right? So this vector here, this is nothing more than y of psi of n. Second one is z of phi of psi of n. And you're subtracting this vector x, which was here defined as the limit of the y's stacked on top of the limit of the z's. Right, so y and z. Right, so basically this is these are two vectors of dimension rk plus 1. So we're going to add 0 to this, a 0 vector, and it's going to be a special 0 vector, as you will see. So we'll copy the first one, phi of psi of n. Make sure that I have enough brackets. And we're going to do minus, so we're going to copy this one. And here we're going to put z. And we're going to add the same thing here. And then minus the remainder, which is this one here, y and z, and put them into norms. Okay, so if you look closely, this is 0 because we're adding and subtracting the same thing. And now, so this is a vector of dimension rk plus 1. This is also a vector of dimension rk plus 1 because it's the sum or the difference between two vectors of dimension k plus 1, and we have a plus. Right, so we have a vector plus another vector. So we're going to use the triangle inequality here. So basically we're going to put y phi of psi of n, z phi of psi of n, minus y phi of psi of n, and then z. Okay, and then plus the norm of y phi of psi of n z minus y z. Okay. So if you would write this out, so this is the norm, right? So it's the square root of a sum of squares, and the squares are taking over the element-wise difference between this vector and this vector, right? The first element of this vector minus the first element of this vector squared, plus second element of this vector minus the second element of this vector squared, plus so on and so on. So all of these differences will be 0, right? Because this vector is the same as this vector. Okay, so we have the sum of a bunch of zeros, and then the last one, you will have the difference between z phi psi n minus this z here. Right, so you will have the square root of a sum of a lot of zeros plus the square of this minus this. Okay, so what you end up with is this is going to be equal to the square root of z phi psi n minus z squared. Okay, and this is the same as z phi psi n minus z, the absolute value. Okay, and then here you have the first element of this vector minus the first element of this vector squared, plus the second element minus the second element here squared, plus the third element here minus the third element here squared, and so on and so on. And then finally the last row will be z minus z. So this is 0, right? So the last element here and last element here is 0. So we only are left with the first case sums and then taking the square root. So what you get here is the difference between y phi psi n minus y, the norm of this thing. Okay, so this is what you have. You have that the difference or the norm of x phi psi n minus x is smaller or equal to this here plus the norm of this here. And what do we know? We know that x psi n minus z, this is a sequence of numbers that converges to 0, right? Because this converges to this. Okay, so this is what we have written here. This sequence here of numbers converges to this. This here is a sequence of numbers, but we know that the y's converge to this y. So this also converges to 0. So we have a sequence of numbers which is less or equal to sum of two sequences that converge to 0. So therefore we have that x phi psi n minus x converges to 0, or equivalently x phi psi n converges to x, right? Because this was the definition of convergence of a sequence of vectors. And if I may conclude, right, x phi psi n is a subsequence of xn, right, and it converges. So we have shown that there's a sequence of xn that converges. Okay, so this was a bit of a long proof, so please allow me to go over it again. Right, just to give the flow of the proof. So basically we prove by induction on k. So P1, if you put k equal to 1, then basically this is the original Bolzano-Weierstrass theorem that you have seen in the lecture. Okay. So for the induction step, what we assume that it holds up to sequences of Rk. If these are bounded, then it has a convergent subsequence. And now we take a subsequence, or we take a sequence of Rk plus 1, which we assume to be bounded. Okay. So this is our sequence of Rk plus 1, and basically what we do is split it up into the first part, which only has k elements for every vector here, and then the last element of this sequence of vectors. Okay, and if you look at the sequence defined by the first k element each time, then this is a sequence in Rk. If you only look at the sequence of final numbers, then this is a sequence in R. Okay, so basically we can split up this sequence of vectors in Rk plus 1 into a sequence of vectors in Rk and a sequence of numbers in R. This is not correct because I'm already in the subsequence, so my papers are a bit mixed up. Anyway, in the first thing, we basically showed that this sequence of y's is bounded, right? Once we have shown that it's bounded, we can use the induction hypothesis pk, right? So we have sequence in Rk that's bounded, so it has a convergent subsequence. And then we restricted this entire sequence to this particular subsequence, right? So for every element in the subsequence, we took the associated number z and therefore the associated sequence of x's. Okay. And then what we said is that once we had done this, we know that the first part converges, but we don't know if the second part of z's also converge. Actually, we don't know if this does, but what we do know is that z is also a sequence in R, and we have shown that it is bounded. So it has a convergent subsequence. So basically, you first take a subsequence along the y's, and then you take another subsequence along the subsequence of the z's. So this is a subsequence of a subsequence, right? So this is why we had the ugly notations of phi's and psi's of things. So finally we get at a subsequence of a subsequence, and for which the first k elements converge to something, and then the last row or the last element of every vector also converges to something. And then it's a simple matter of adding and subtracting the same thing to show that if the first part here converges to this and the second part here converges to this, then also this converges to 0. So x phi psi n converges to x, and x phi psi n is obviously a subsequence of the original sequence, which shows the Bolzano-Weierstrass theorem for sequences. So far for this lecture.